Guys, it is 7:06, so let's get started. For those of you that maybe you just came in, I don't want you to worry. We're still gonna do the whole 2017 exam. Don't think you missed the whole thing and he was doing synthesis. Okay, we just wanted to do a little bit of synthesis at the beginning, so you're ready for that. And then also, I asked in a poll in the group me of I don't know how many people, but I asked do you guys want to do nomenclature first and then go all the way through like I normally was doing, or do you prefer to start with facts and then come back to nomenclature? And it was 50% the whole weekend, and then today 4 people I guess voted for normal. So I'm gonna go with the people, right? So we're gonna just do it normal, but hopefully our video is gonna work. So for your friends that weren't able to make it, or even if you have to leave early and you want to still see the synthesis, it will be uploaded, okay? And we have 2 cameras, okay? All right, so we'll start with nomenclature. Okay, so for nomenclature, in Orgo 1, now we've introduced different functional groups, right? So we've introduced the alkynes, we've introduced the, is it good? Yeah. We've introduced alcohols, right? So in terms of our priority, we've added some things. So I'm just gonna put, ooh, that's really thick. All right, so in terms of priority, what's going to be at the very top? It needs to be our alcohol, okay? And then right below alcohols, what are we going to have? Alkynes, and with the alkynes, its partner is going to be alkenes, okay? And then at the very bottom of our totem pole, what are we going to have? We're going to have our bromides, right? So halogens, all of that. We're also going to have just our regular alkyl chains, so methyls, ethyls, all that, right? And then what else are we going to have? Those are the 2 big ones. And if I think of any others, I'll add them, okay? So what we want to do when we're looking for our parent, you want to pick the longest chain you can find that includes your highest priority functional group. And that is our alcohol, okay? That is we need to be focused on that, okay? Ignore all the other stuff that's going on. Find that alcohol or that alkyne or alkene and make that your parent, okay? And we want it to be the longest chain. So looking at our first question, no alcohols, right? So our next in priority would be the triple bonds or the double bonds, right? So we're gonna wanna find the longest chain we can that includes those 2 things, right? They're equivalent when we're doing this priority. So of course it's gonna be this 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So our prefix for 9 is gonna be non. So on the side, I'll write parent, and that's where I'm gonna write non, okay? Now we want to figure out, how are we going to number this? Are we going to number it from left to right or right to left? So let's put on the side, left to right or right to left, right? And you want for your highest priority groups that are making our parent, we want for those to be on the lowest number that we can put them on, okay? So if we go left to right, we would get our alkyne at number 2, right? And then let's keep going. 4, 5, 6. And we would get our alkene at 7, right? Okay. And let's say we went the other way. Okay. If we were to go right to left, you would go 1, 2, 3, 9, right? So our numbering for this would be alkene at number 2. And then our alkyne at number 7. So now we have a problem, right? So it's the same no matter which way we go. All right? So which one now is going to take priority to put it on the lowest number? Alkene or alkyne? I heard both. Okay, so let's look at alphabetical, right? Ene, Ein. Which one comes first? E. So whenever you have a tie in between these two groups that are equivalent in terms of priority, right? Whenever you have a tie, you're going to put the double bond on the lowest number, okay? So that's what we're going to go with. So that, which way is that going to be? It's going to be the way from right to left. And that's the way that I have it numbered right now, okay? Alrighty. So now we have to indicate where are these groups coming off, now that we have the numbering. So we have 1, 2. So you're going to have our number 2 carbon, right, has a double bond. So that's going to be En, so non-2N. And then after that, we have our triple bond. And our triple bond comes off of which carbon? 7. So we're going to put 7, right? We're not going to put an E after the N right here. Okay, because there's still left. There's still the triple bond. Okay, 7, ein. So if it was the end of the molecule, then we would end it in non-2-ene, right? But we still have the triple bond, so we're going to end it with ein. Like that, okay? So we've dealt with our parent. That looks okay. So now that we dealt with the parent, we can look towards the substituents. Yeah.
Can we have it 2 non-ene 7 ein?
2 non-ene 7 ein. Yes, you can put this 2 right in the front if you prefer to do that, for sure. That is perfectly fine. Okay, so our substituents. Right. So what do we have coming off of this parent chain? We have this group, okay? This is a ring, so we're going to have to include cyclo, right? And then you ask yourself how many carbons, and it's 6. So cyclohex, and it's a substituent. So you add YL, right? You don't make it cyclohexane. Cyclohexyl, and then you ask yourself which carbon from the main parent chain is it coming from? And that carbon is going to be our number 5. Okay, so are we done?
We need to check for stereochemistry.
Exactly, very good. So we have to, what he said is we have to check for the stereochemistry. So on the side, we'll put stereo, right? And do we have any chiral centers? Well, we do, but like this right here. It's not showing us wedge or dash, so we don't have to do R or S for that one, okay? But we do have something else, and that's the double bond, okay? So for the double bond, we have to show where are these groups coming off of the double bond. And that's going to be E or Z, okay? So what we're going to do is we're going to cut the double bond in the middle, ignore the right side. Just look at the left side, okay? And compare the groups that are coming off of that carbon. So I'm talking about this carbon right here. What do we have? We have a hydrogen, and then we have this long alkyl chain. So which one is higher priority? The top one, right? The top one is a carbon attached to carbon and a bunch of other stuff. And then the hydrogen is just a hydrogen, right? So if you have any questions about the priority, how to do that, like Chance, or we don't have any tutors yet, but Chance will come to you and help you, okay, on that. So the heavier one is going up. So I'll put H going up. And then for the other side, we have hydrogen, right? And methyl. So which one's higher priority? The methyl. So our heavier or higher priority group is going down. So those H's are representing which one is higher priority, not hydrogen, okay? So they're going in opposite directions. So is it going to be Z or E? E. Good job. Okay, and we only have one internal double bond, okay? Since we only have one internal double bond, we don't have to indicate that it's coming from the number 2 carbon, but if you do put it, you shouldn't get any points off, okay? In fact, for my exam, I put 2E, and they just put a little X on it, but they didn't take off any points, okay? But it's implied that you have only one internal, so it's okay. So when we're going to write this out, we'll put in parentheses like this, right? Dash, we're going to a number. So cyclohexyl. We're going from letter to letter, so no space. Non, 2, N, 7, ein. Okay? Do you guys have any questions about that?
So what if it wasn't going to say number exactly? How is
Okay. So she asked, what if it wasn't 2,7 and 2,7? Which one will be higher priority? So you will consider them the same, and you just group them in a group, like alkynes and alkenes, and you find the lowest number. Okay, and you take it that way. All right. The only reason why we checked for the alkene to be lower was just because we had a tie. That's a really good question. Okay, so if you have any other questions about that, Chance will come to you. And we'll move forward, okay? So for the next one, same idea. We're going to want to find our parent. Okay? And our parent is going to be the longest chain that includes our highest priority group. And our highest priority group is what? It should be an alcohol, exactly. Okay, so here we have two OHs in the molecule, but we're going to go with, so we're ignoring the triple bond. That's very key, okay? If you don't do that, then you'll get the parent wrong. We're looking only at our highest priority, which is the alcohol. And we're going to find the longest chain that includes the alcohol. And that would be the one that's a part of the ring, right? If you count the other 1, 2, 3, 4, 5, right? Versus the ring is 6. So we're going to go with that one. And we're going to pick that as our parent, so I'll highlight it like this, right? And so this is called the benzene ring. And whenever you have a benzene that has a hydroxy group like that, the OH, you're going to call it phenol, okay? So that's like one of those things you just have to memorize, but it's not too bad. The ol, OH, right? Phenol just is representing a phenol, like a benzene ring, okay? So that is our parent. I'm going to include it like that. I kind of highlighted it. Okay, and now we want to number our parent, right? So around the ring, by default, the alcohol, highest priority, it has to be our number 1. It has to be. So we're going to put this our number 1, okay? Right? And that's why, one student asked about this, that's why you don't put any numbers right over here, okay? It's just phenol, because when you have a ring, it's assumed that it's your number 1 carbon is the alcohol, okay? So then you go around and you want to get the lowest number. No matter which way you go, you guys, you're going to get 1, 4, right? So it doesn't matter. You pick whichever way, okay? So then we want to name our substituents, right? And so we have a substituent coming off of the number 4, and we're going to do the complex naming for that one, okay? So we take it to be its own pseudo-parent, right? Cut it like that. And the first carbon that's attached will be our number 1 carbon, okay? We go 1, 2, 3, 4, 5. Okay, so when we're doing our prefix, 5 is going to be pent, right? So you put pent. Okay. But then you also have to account for these things that's coming across what's present there, right? So we have the hydroxy, we have the triple bond, okay? So when we're doing the substituents, you want to make sure to include the ine part. So that's going to be 1, 2, 3. So at our third carbon, right, we have the triple bond. So 3-pentynyl, like that. This is an N. And then we also want to account for our hydroxy group, right? So whenever the alcohol is in a substituent, you name it hydroxy. Like that, okay? Then we have to indicate where is that hydroxy located in our pseudo-parent, and it's coming from the number 2 carbon. So we put it like that, okay? This is a complex substituent. We put parentheses around the entire thing to group it together, and then you ask yourself, where is this coming from our original parent? And our original parent, it was coming from the number 4, okay? So that's all our stuff. Do we have to worry about stereochem? There's no stereochemistry, right? Triple bond, there's no chiral centers with wedge or dash being shown, so we're just going to write this in our box. And no space, no dash in between the L and the, or between that parentheses, close parentheses, and the phenol, okay? Do you guys have any questions about this? No? Okay. So let's do the last one. And remember, the first thing we're going to do is find that parent chain that has our highest priority group, and that is going to be our alcohol, right? So here we have an alcohol, but we have that OH, but we also have the double bonds. And this is actually, let's look at it. Is this symmetrical? Yes, it's symmetrical. So really it doesn't matter which way you go, but you just want to make sure that your chain that's the longest has that hydroxy in it. Right? So you're not going to pick the horizontal flat chain, okay? You're going to pick the one that includes that OH in there, okay? All right, so now we're going to ask ourselves, how many carbons does this have? Bless you. Okay, so it's going to have 1, 2, 3, 4, 5, 6, 7, right? So our prefix is going to be hept. But hept like that, right? And the reason why I numbered it in that way particularly is because the alcohol is our highest priority. And so even if you went the other way, right, the double bond is on number 1. But our priority is our alcohol, so we're ignoring that double bond. You want to put that hydroxy on the lowest number you can, okay? So that would give us 2 for that. So, yeah.
Also need to have the least amount of substituents.
So I wouldn't focus on that yet. I would focus, so let's say you get down to a point where you do have a tie and everything is tied, and you have to pick one way, gives you more substituents, that's the way you want to go. Does that make sense? Okay, so we said that it's hept, and we have this double bond. So in our parent, we're going to want to indicate that double bond first. And so it's going to be hept. And where is the double bond located? It's located at 6, and it goes hept 6N. And then now we still have to indicate where is that OH coming off from, right? And it's coming from the number 2. So we're going to put 2. There's only one of them, so it's going to go all like that, okay? So that's our parent, okay? And now we can move forward, ignore our parent, and we're going to go on to our substituents. And we only have one coming off, and that's at our number 3 carbon right here. So I'll circle that, right? Consider it to be its own pseudo-parent. So you're going to go 1, 2, 3, 4. So you write subs. And our prefix for 4 is going to be but. Okay. And we have a double bond. And that double bond is at number 3. I'll put butenyl, like that, butenyl. And it's coming from our number 3 carbon. So I'm going to put 3 like that. And then do we have anything else coming off from there? No. But we do, this is complex naming, so we have to put our parentheses and indicate where is that coming from our parent. And it's coming from the number 3. So I'm going to put 3 like that. Okay? And are we done? No. What do you have to account for? Yeah, RNS, the hydroxyl group, that's a chiral center. Very good. So this is a chiral center. So we're going to put stereo like that. And we're going to find RRS. And we're going to judge it based upon the atomic mass or atomic number and which one's highest. So our highest one is the oxygen. So you put that as our number 1 in the circle. And then next we have this carbon coming down right here, the one that I put a dot. That carbon attached to carbon and carbon. So that's going to be our number 2 going down. Then we have the methyl group. That's going to be our number 3. And of course, our hydrogen is going to be number 4. Draw our arrow on the paper, 1 to 2 to 3, right? And that is S. The counterclockwise is S. And then we only have, and our hydrogen is going away from us, so we're good, okay? If it wasn't, then we have to swap it. Now, we only have one chiral center, so it is A-okay to put it as just S and not indicate the number. If you had more than one, then you want to indicate the number, okay? So we can write this entire thing in our box. All right, so any questions about nomenclature? I'll zoom out so you can take a picture if you want to. Any questions? All good? Okay, good job. All right. So now we're going to move forward to facts. Blank page. Okay, so for this question here, it's asking about the alkenes and which one is stable and which one is unstable, okay? So if you notice with all three of these, they all have more than one ring, right? So they're bicyclic. And what's special about these is something called the bridgehead carbon, okay? And the bridgehead carbons are going to be those two carbons, like the name kind of tells you. It's the carbons that are anchoring the bridge from either side. So I'll point to them right here. For this one, it would be this carbon and this carbon. For the middle one, it'll be this one and this one. For this one, it'll be this one and this one. Okay, so those are our bridgehead carbons. And why are the bridgeheads important? The reason why they're important, and when we're talking about stability, is because if you have a double bond, right? So one of those bridgehead carbons, if you have a double bond participating in one of those bridgeheads, you want to make a comment?
What flipped? Oh, wait. I don't know why. Oh. They just wanted you to zoom back in, that's all.
Oh, yeah, of course. Just ask. Okay, so if you have those bridgehead carbons participating in the double bond, right, you got to check about the ring. And you have to follow something that's called Brett's rule. So I'm going to scroll up here and write Brett's rule. Okay, so if double bond, right, is on bridgehead, then there must be a ring greater than 7, okay? Equal to or greater than 8, right? So that's Brett's rule, all right? And this is talking about bicyclic rings. So that's what we're gonna follow when we're doing our questions. So the first one, does it have a double bond participating in one of those bridgeheads? No. So our answer is gonna be stable. That's it, okay? And then we move forward to the next one. Do we have a carbon, right? The bridgehead carbon, is that a part of a double bond? Yes. So now we have to apply the Brett's rule. We're going to look at all the rings that are present in this molecule, not just the one that includes the bridgehead. We're going to look at all of them and see if we can find one that is 8 or more. All right, 7. That doesn't make the cut, so we're going to erase it. Okay. And if you count the other way, like, it's going to be the same thing. Like that, right? Also 7 doesn't make the cut. Okay. And then, of course, this one, just by the look of it, we can tell, right? This is definitely not 8. So what are we going to say? Stable or unstable? Unstable. Good job. Alrighty, so then we're going to look. Oh, yeah.
What do you mean by make the cut?
Like it's not 7. It's not greater than 7.
If it's greater than 7, then it would be stable?
Yes, exactly. Good job. So then for this one over here, let's do the same thing, right? Bridgehead carbon involved in double bonds. So we got to do Brett's rule. We're going to go 1, 2, 3, 4, 5, 6, 7. Okay. That doesn't work. Now let's do this one. 1, 2, 3, 4, 5, 6, 7, 8. Ring, ring, ring. That is stable, okay? So the answer is S. Okay, we got to 8, and that's what we want. Any questions?
So it's greater than or equal to 8?
Greater than or equal to 8 or greater than 7? Exactly. I like to say greater than 7 just because the greater than kind of looks like a 7. So if you forget, greater than 7 looks like a 7. Say that, my girl. What's up?
Can you do the first one again? Like I mean,
The first, this one right here? Yes. So is the bridgehead carbon, is that involved in a double bond? One of those two that I have asterisk? No. So it's stable. Right away. Yes. Good question. Okay. So now we'll move forward to number 2, and it's asking us to rank the electrophiles in order of increasing electrophilic character. 1 being the least and 3 being the most. Oops. We have an answer already shown. Y'all didn't see that. Alrighty? So when we're comparing between these, we want to pick the same point of difference between the molecules, right? We're going to look at the same carbon or whether it's comparing a hydrogen. We want to look at the same point of difference, okay? So we're going to look at something that's common between all of these. They kind of all look similar, right? If you consider these to be analogous to one another, right? Those carbons that I have kind of put the dot on top of, okay? An electrophilic, right, something that likes electrons, if something likes electrons, it likes negative charge, it itself has to be what charge? Positive, exactly. So we're comparing and we're asking yourself, which of the following is the most partially positive, right? None of them has a full positive. So when we're looking, the 2 on the right are both carbonyls, okay? So all of these are going to have a dipole moment via that sigma bond like this, making that carbon partially positive. But the difference between the ones that have the carbonyl and just the hydroxy group is that, remember resonance, if we were to show some resonance here, what do we have with those pi electrons? I'll erase it so you can see. This could come onto the oxygen, right? So if that were to happen, I'm going to draw it coming from this one, just so I don't have to draw as much. Right? If that were to happen, what would our resonance structure show? It would show positive charge on that carbon, right? And we said that only the hybrid exists, right? So our hybrid is going to have a little bit more cationic character than the normal because of that resonance structure, right? Those electrons can go up onto the oxygen, and that makes this carbon a little bit more partially positive, okay? So right away, because of that fact, we can put this one that I marked like that and hit it. That's our number 1. Okay, does everyone see that? Now we're going to compare between the 2 carbonyls, right? We're looking for the one that is more positive between them. The one in the middle, what's the only difference? Is that it has chlorines, right? Is chlorine electronegative? Yes. So if it's electronegative, that means it's going to pull electron density towards itself, right? And take it away from that carbon. And there's 2 of them. So this is the inductive effect, right? And so for that reason, it's making this middle carbonyl carbon more partially positive, and that's what we're looking for. So that's going to be our number 3. And then the one on the right will be our number 2. Okay? Any questions? No? Okay, good job. So let's go to number 3. Okay, so it says place a Y in the box below any compound that will produce a terminal alkyne, when treated with NH2, so sodium amide. This is a strong base or a strong acid? Base, really good, very strong. Strong base. Okay, at 150 degrees Celsius, place an N in the box below, any that will not. Okay. So I'm going to zoom out. Okay, so our strong base, we said, NaNH2, right? Don't let the sodium fool you. It's just a spectator ion. Like this. So it's balancing out the negative charge that's on that nitrogen. I'll draw the entire thing. So this nitrogen, in order for it to have a minus charge, it must have 2 lone pairs, okay? So this right here is a very strong base, very strong. Okay. And it's so strong that it's able to come and deprotonate. Let's make this an R group. It's able to come and deprotonate this proton, right? It's not very acidic, but it is acidic enough for this very strong base to come and deprotonate this, okay? So that's the reason why a lot of people ask, like, why does NaNH2 give the terminal alkyne? And this is the reason why. So this will give us a terminal alkyne, okay? Just wanted to explain that part. Now, how can we create an alkyne? We have to start with digeminal or divicinal or vicinal dihalides, okay? So that just means that on 2 carbons, you're going to have a halogen, that's the halide part, and you're going to have them adjacent on adjacent carbons like this, okay? We're trying to create a triple bond, right? So this is vicinal dihalide. So what does vecino mean in Spanish? Does anyone speak Spanish? Neighbor. So they're on neighboring carbons, right? So if you have geminal dihalide, it means that you're going to have it on the same carbon, okay? You need one of those, so you need this or geminal, in order for this strong base that we had to come. This is E2, okay? Remember E2, all in one step. This comes here, boom, leaving group leaves. It's going to happen another time, right? Let's take another one. Happens again, abstracts the hydrogen. Electrons go onto this bond, bromine, good leaving group, leaves. Form triple bond, okay? And it's going to give you the terminal one. So what you need is you need vicinal dihalide or geminal, right? Like this. And you need those carbons, right, to have hydrogens. If they don't have hydrogens, it's not going to be able to do E2, okay? So that's what we're going to be looking for when we come down and we do this one over here, okay? So let me draw in our hydrogens. Okay. So for number 1, given what I just told you, are we going to be able to have these 2 elimination reactions happen? We have one hydrogen adjacent. We have another hydrogen adjacent to our geminal. They're coming from the same carbon, from our geminal dihalide, okay? Because we have that, this will get abstracted, this will come down, this will leave, and then the same thing will happen again. So our answer is going to be yes, okay? It happens. Now, let's look at the next one. You take the 2 carbons, right? We have a geminal dihalide, so that's good. And then look at your adjacent carbon. We have 1 hydrogen. We don't have 2. So is it going to happen? No, because elimination is happening twice, right? So you need this bromine to be adjacent to a hydrogen, and you need this bromine to also be adjacent to a hydrogen. But it's not. So for that reason, we're going to put no, okay? We'll look forward to the next one. So we have the vicinal dihalide, right? And we have these hydrogens, okay? So are we going to be able to have our 2 E2 reactions happen? Yes, exactly. I think you guys are getting the hang. Oh, that's a very good question. Oh, I'm glad you guys brought it up. Yeah, so what's special about this NaNH2 is if allowed, it will go and have this rearrangement in order to give you the terminal alkyne, okay? And so it will do that and will allow it to go to the terminal ends, okay? And so the 2 bases that are involved in the creating of the alkynes, you're going to have either the sodium amide like I just showed you, or you're going to have KOH like this. You're going to have KOH, and what temperature? Does anyone know? 200. Good. Or you're going to have the sodium amide like this, and we're going to have it at a less high, like a lower temperature, because it's stronger of a base. This one is going to give you internal, okay? It's not strong enough and able to do that rearrangement. This one will do that, and it will give you the terminal double bond, okay? So it will do that, even though the dihalide is not located at the end of the molecule. And right here, a way to remember this is I like to tell students, if you look at the sodium amide, this little 2 here, it's kind of hanging off the terminal end. So it's going to give you the terminal alkyne. Okay? Just a little trick. Okay? So that's going to be yes. Okay, so let's compare this one. Bisphenol dihalide, that is good. And then we have a hydrogen here, right? And then you're comparing this, this, and this. So does this carbon over here, does it have a hydrogen to abstract? No, exactly. That carbon already has 4 bonds. It's neutral, 4 bonds, no hydrogen is located there. So for that reason, we're going to say that the alkyne cannot be produced. So the answer will be no. Okay? Yes, it can. As long as coming off from the sides here, we have hydrogens. Right? Then we're good to go. It will rearrange to go all the way to the end. Okay? Well, after you form that alkyne, the mechanism for this isn't important for you guys to know, but one of the hydrogens will be abstracted. It will rearrange and make its way all the way to the end. Okay? As long as that there's hydrogens adjacent. Like that. Okay? And is Chance here? If you have a question about that in particular, like maybe Chance can come and explain it better than I can. Or go more into depth. Okay, so we'll do number 4. And it says, place the compounds in order of increasing oxidation state, 1 being the lowest and 3 being the highest, okay? So you really need to know what's the meaning of oxidizing something and reducing something, right? So remember like your oil rig from the Gen Chem. So in the orgo, it's a little bit of a different definition, and I think it's even more straightforward, that oxidation is just going to be increasing the number of bonds to what? Oxygen. Oxidation, right? That's why it sounds like oxygen. So bonds to oxygen. It could also be nitrogen. So if you're in Milianic, he likes to use, or Dr. Milianic's class, he likes to show nitrogens on there. Sometimes the halogens as well. But for Dr. Bean, typically it's really just oxygens that she's going to be showing there. But it could be one of those. So you're increasing the number of bonds to one of those 3, okay? Very electronegative things. And then you could also be decreasing number of bonds to what? To hydrogen, right? And then reduction is going to just be the opposite of this, okay? So we're looking for our most oxidized of these 3. All right, comparing these molecules. So which one has the greatest number of bonds to oxygen? Yeah, at the right end. Exactly. So that's going to be your number 3. Which one has the second most bonds to oxygen? So that's going to be your number 2, second most oxidized. And this is going to be your number 1. Okay. The number 3 is a carboxylic acid. The number 2 is an aldehyde. And the middle one is just an alcohol, okay? So later, like in reactions, when you're doing the oxidizing reagents, you're going to be going between these things, okay? All right. Do you guys have any questions about that? No? Okay. Now, this is really important. Number 5, I think, is the most important. So whenever you see the word Grignard in Orgo 1, that's probably arguably the most important thing you're going to learn in Orgo 1, okay? So I'm going to use this page over here. We'll talk a little bit about Grignard. Okay. So what is this thing called Grignard reagent? And, okay, so it's asking us to place a Y in the box below any compound that will react with a Grignard reagent. Place N in the box below any that will not. So firstly, what is a Grignard reagent? Grignard reagent is an example of something that is a very, very, very strong nucleophile. So you take any carbon group, right? And it's going to be attached directly to this magnesium metal. And then from the other side, you have a bromine, okay? And so think about the bond between a carbon, so that R group, and the magnesium, right? You have a metal with a nonmetal, right? So that will have some ionic character to it, right? It's drawn as a covalent bond like this, but it is very polarizable, meaning that there is a huge difference in electronegativity between the magnesium and that carbon, okay? So due to that fact, the electrons are going to lie towards which atom? Carbon or magnesium? Which one's more electronegative? Carbon or the magnesium that's at the very far left of the periodic table? A metal versus a carbon. The carbon's more electronegative, exactly. The metals that are in those two groups at the left, they want to actually lose electrons, right? So it's the opposite. So it's going to lie more towards the carbon, okay? So if we want to draw this in another way, let's put the R group and say that those electrons are basically belonging to that carbon. So it's like a carbanion, has like a character of a carbanion, right? And then the magnesium, it's on that second group in the periodic table. So what charge it would gain is a 2+. Then you have a bromide, and bromide likes to have 1-. So you guys see how the charge is just balancing out? It's just neutralizing the charge. And so that's why it's going to be written like this. But you don't let that fool you. This carbon has a lot of excess electron density. And minus charge on a carbon is not stable, okay? So this is a strong, insanely strong nucleophile, okay? So what does that mean? Nucleophiles like to attack what? Electrophiles, exactly. So that means this Grignard is looking to go and attack some electrophile, okay? Anything that is partially positive enough, it will go and react with. It will go and attack, okay? So an Orgo lab, for those of you who have taken the Orgo lab, you're going to spend like 6 hours trying to make this Grignard, and if you get 1 drop of water on it, it's gone, you know? So we want to just make sure that in this question, when it's asking, place a Y in the box below any compound that will react with a Grignard, that means things like water, right? Anything with an acidic proton on there, anything that has a strong enough partial positive charge, it's going to react with it, and it's going to ruin the Grignard that you just spent 6 hours to make. It really sucks. So that's what we're looking for. We're looking for things in this question. We're looking for things like this is a carbonyl carbon, right? So it's partially positive, like we discussed in the previous question. We're looking for even this is partially positive enough. This hydrogen is partially positive enough. This is partially positive enough. If you have, for example, a nitrogen, anything electronegative attached to hydrogen, like that, these are partially positive enough. Grignard will boom, it will go and attack with it. Okay? We'll look at more examples in this question here, okay?
So it's a hydrogen bond, right? What we're looking for.
So what you're looking for some atom on the molecule. It doesn't have to be a hydrogen, but most likely it would be. That's partially positive and electrophilic, right? So if you have, for example, like even in water, right? We're talking about water before, right? These are partially positive enough, right? And you also have some hydronium. And then even if you have something like, an alcohol, right? Right? This hydrogen is partially positive enough, right? So it's going to react with something like that. So yeah, if you're looking for something that can form hydrogen bonds, most likely that's something that is partially positive enough for a Grignard to go and attack. Yeah. Okay. So we're looking for the one that's going to react with something partially positive. Instead, basically, we're normally trying to use it with a carbonyl carbon, right? That's what we want our product to be. We want the Grignard to go and attack here. But if on our Grignard or on anything in the mixture, if you have that partial positive, it will go and react with it instead. So we're going to look at the first one right here. We have a nitrogen. Nitrogen has lone pair, right? there's a dipole moment between that nitrogen and the carbon beside it, right? There's partial positive here. You can even do a resonance structure as well. So is this going to react with a Grignard? Yes or no? Yes, because of this partially positive carbon right there that is attached to a very electronegative nitrogen. Okay? And then what about this one in the middle? Is there anything acidic or electrophilic for the Grignard to react with?
Yes.
Exactly. So that's what we discussed right down here, right? Right here. It's going to go and react with that instead of the carbonyl we wanted to react with. So for that reason, we're going to say yes. Okay, what about this one over here? Anything that's partially positive? Anything electrophilic? No, not at all. In fact, the double bond likes to act as a nucleophile. So a strong nucleophile is not going to go react with something just like itself, right? So the answer is no. Okay. And then for this number 3, any carbon or any atom that is partially positive enough?
Yes.
Which one?
Wouldn't it be the ones that are close to the oxygen?
Yeah. So that's a really good question. Now let's go down here and ask ourselves, this is a reaction question. So how do we make a Grignard? Right? So if we have this, for example, and we have an alkyl halide, and we're trying to create a Grignard, what are we going to put on our arrow? What reagent? Mg ether, yes. Exactly. So we're using an ether in order to make this, right? So if we typically use an ether to make this, right, and in this molecule here, we have an ether, does that mean that it would react with it? The reason why we use the ether is because it is anhydrous enough in the sense that it's dry enough, right, as opposed to water, for example, that's the reason why we use the ether. So whenever you have a question asking, will the compound react with a Grignard reagent, and you have an ether, so if you're asking about what an ether is, it's just an oxygen attached to 2 R groups from either side. I like to call this our ether bunny, right? Those are their whiskers. That's our ether bunny. Okay? So this does not have any sites that are partially positive enough. Okay? Those dipole moments are actually being canceled out by one another. It goes the opposite way. Okay, so just remember that we use the ether to make the Grignard. So we wouldn't use the ether to make it if it would react with it, you know? So for this reason, when it says no, so it will not react with the Grignard. So we'll put it in. What about this molecule right here, the SH? Do we have any acidic in parts of that molecule? Yes, which one? Where? Yes, so there's a dipole moment between the sulfur and the hydrogen due to the difference in electronegativities. So yes, this is going to react with a Grignard. No good. Okay, and then what about this one? Anything partially positive? So this one is like the toughest one, I would say, out of all of these, because you're not seeing a charge drawn for you, right? This group over here, you'll talk more about it in Orgo 2, but for right now, all you have to know is this is called the nitro group, right? And if I were to draw the nitro group out for you guys, I'll draw it right below it. So take this. So it's, when we have it in that structure, they're not showing, right, any positive, any negatives. But don't let it deceive you, right? So this benzene ring is attached to a nitrogen, and that nitrogen is attached to 2 oxygens, right? So we'll put, this is what the structure will look like. Right? So what is the charge on that nitrogen? Positive, right? Because you have 1, 2, 3, 4 electron groups, 5 minus 4, 1. So there is a full-on positive charge on that nitrogen, but it's not being shown here. Okay? So don't let that deceive you. If you see the nitro, it really looks like this. Okay? Full positive charge on that nitrogen, so is it going to react with a Grignard?
Yes.
Exactly, yes. Okay. So that's for that one. Do you guys have any question about this? This is very, very high yields. This will very likely show up, okay? And read the instructions very clearly. It's gonna ask you, will it react or will it not react? And a lot of students will flip the answers, okay? I think I saw a hand. Did you guys have a question? No? Okay. Does anybody have a question about any of these? Yes, exactly. So he asked if there will be questions that ask if it will be a good Grignard reagent. Exactly. That's another form of asking the same concept, right? So if there's no electrophilic sites on there, then it would be a good Grignard reagent. You don't want it to come and react with itself, right?
And another way would be if it's a very strong liquid.
What do you mean?
If the Grignard reagent is a strong liquid.
Very strong. Yeah.
And that's going to be, we have like this chapter 6, I think that's what is a strong file. We can go by that.
So in chapter 6, they didn't discuss the Grignard strong but they gave a list of like strong liquids, and whenever you have a carbon and minus charge, it was very interesting. Okay, you guys, so if you want to take pictures of this right here, can you see it or you want me to zoom in? Where's Chance? Where's Chance? I want to know. There he is, my guy. So is there anything you want to like tell the students, like a commonly asked question, FAQs?
Not really. The only thing, so that Grignard question was asking whether Grignard will react. On most of the old exams, it's asking whether or not it will create a useful Grignard reagent. So that's a totally different question. A lot of you were answering the question as if it were which will produce a useful Grignard reagent. So just keep in mind to read the directions. She may change things up on you.
100%. 100%. That's exactly what I was saying, because I remember this exam in 2017, and a lot of people, a good amount of people, they wrote the opposite. They were answering the opposite question, and so they got everything correct but for the opposite. So that's like the whole thing wrong, you know? And a lot of people did that, you know? So read it really carefully and don't assume that it's just like an old exam, okay? Did you have a question? No? I thought I heard Sabrina. All right, you guys, break is over. We're gonna be serious now. Okay, so we'll start with reactions. This is my favorite section, okay? And I'm gonna try, I know it's a lot, but I'm gonna try to give you guys tricks, right? In order to remember some of these that are tough to remember, okay? And I'll talk about the mechanism if it's going to help you to understand it, or if you're required to know it, then I'll talk about it, okay? Okay, so let's start with number 1, right? We have this molecule that has a hydroxy group, and then we have H2SO4 in heat. So is H2SO4, is that an acid or is that a base? An acid, yes. So I'm going to put, it's a strong acid too, so I'm going to put strong acid. And every time you do these, you guys, write what you know about the reaction, okay? I know it's a lot, but just write as much as you know about it, and that's practice right there, okay? Even if something's not necessarily related, relate it to something else, okay? So that's a strong acid. We have it in heat. So the heat should also remind you of SN1 and E1. Remember, we needed heat for both of those? So this reaction here could just be E1. So let's look at it. You have this hydroxy group over here with the lone pairs, right? And so what is that going to go and react with what's on our arrow? I'm asking, what is this oxygen right here? What is that going to go and attack on our H2SO4? The hydrogen, exactly. So that's our acidic part of this molecule. So it's going to go and boom, attack that. Electrons will go onto the oxygen, okay? So when we do that, we're going to protonate that oxygen, right? We abstracted that hydrogen, And now what charge does the oxygen take? A full positive, okay? Now, this alcohol is attached to a carbon that is tertiary, right? So that's good, that's stable. So in the sense that if our leaving group, we formed a leaving group, this is water. So if it leaves, it's gonna be water, and water is neutral, right? No charge there, very stable. So if this were to leave, electrons go on to the oxygen, you form H2O, and then what remains on that carbon is a full positive charge. So what we get is a carbocation. In our carbocation, so I'm gonna erase that left as water, good leaving group. Our carbocation is 1, 2, 3, it's tertiary, right? That's the most stable, but we can get it, okay? Now, what we're gonna do is we have these adjacent hydrogens, okay? And this is going to be like an E1 reaction. This is E1. You just had to form that leaving group on your own. You form the carbocation, intermediate, and then your conjugate base, right? Or even if you were to have some H2O in the mixture, will come and abstract one of those two hydrogens and push the electrons onto the sigma bond to form a double bond. Remember, E1 forms double bonds, right? Okay, so now you need to ask yourself, which one is it gonna go and attack? So our base, we're gonna just put B, but this would really be the conjugate base, right, of this H2SO4, okay? I'm just gonna put B though. So is it gonna go and abstract this one, okay? Or is it gonna go and abstract this one? This is A and this is B. What do you guys think? A. So if it were to go and abstract A, this is how you got to think about it. So if it were to go and abstract A, you would form the double bond right here, right? You see the dotted line that I put? Right? So what is the substitution of that alkene? Like, is it tri, or is it di, or mono, or... Yeah, it's going to attack HB, but this alkene right here, is it tri or di or tetra? Tri, okay? So like when I'm counting, and I'll put it in a highlighter. So this right here is one bond to that double bond. This right here is another bond, and then this right here is the third one. So if that hydrogen A gets abstracted, you would form a tri-substituted alkene, okay? So I'll write tri on the side. This is how we're gonna decide which one. Okay, if the base comes and abstracts hydrogen B, right, pushes these electrons onto that sigma bond, what would our substitution be of that alkene? Tetra. So I'm going to highlight that in a different color. 1, 2, 3, 4. That's where he's getting tetra from, okay? So you have to ask yourself, which one is more stable, tri versus tetra? Tetra. Tetra is more substituted, so tetra is more stable. So you're forming the more stable product. So the hydrogen that will get abstracted is hydrogen B. Okay? And that's where we're going to put our double bond, on the hydrogen B. Or, you know what I mean. Okay, does everyone see that? Okay, and then for number 2, you guys have to recognize, I shouldn't have done that, but you guys have to recognize that this is ozone, right? O3 is ozone. Okay, so what the reaction happening here is called ozonolysis, or ozonolysis, sorry. Accent. So ozonolysis, and then you have this dimethyl sulfide, right? So the mechanism for this, you're not expected to know it, but you do have to know that 2 and 3 are combined together. So when you're writing your arrows in the exam, make sure that you put 2,3 or 2/3 on the same arrow, okay? You're not expected to know that mechanism, and I don't think it's fully understood, actually. I'm not sure. But what you do have to know is that, like the name tells you, lysis, what does that mean? You're cutting something, you're lysing something. So that's exactly what we're going to do to our molecule. You look at your functional group on the molecule, and you have a double bond. It's boom, it's gonna cut that right in the middle, okay? And remember, ozonolysis has all these O's in there, so you're gonna put an O right here and an O right here, all right? And I'll show you what I mean by that. You're gonna basically create 2 carbonyl carbons. So this is that double bond, you get, right? So I just cut it, put the carbonyl at that carbon, and then the other one, I did the same exact thing. Cut it, put the carbonyl at that carbon right here. Okay, that's cleavage, it's oxidative cleavage, okay? And you just get 2 ketones, right? So that's what's gonna happen for steps number 2 and 3. They go together. Okay, and now we have on number 4, we have this what's called acetylide anion, right? So is this gonna be a strong nucleophile or strong electrophile? Nucleophile. How did you know that? Negative charge. So you have a full negative charge on a carbon that's not stable, excess electron density, so that's going to be a nucleophile. So this is going to come and attack some electrophilic sites that you have on your molecule. And where is that? The carbonyl carbons, right? And we have 2 of them, right? So this is very similar to a Grignard, where a Grignard would do the exact thing, come and attack. Right here, this electrophilic site, push the electrons onto the oxygen. Okay, so I'll draw what that gives us. Right, so the pi bond went onto the oxygen, so the oxygen will now have a minus charge. Right, and the same thing happened to the other side. Pi bond became lone pair, so you also get a minus charge. Right? So that's our step number 4 so far. But then remember, after this comma, we have then H3O+. Is H3O+ acid or base? Acid or base? What do you think? Acid. Yeah, it has a positive charge there. So what's going to happen is all that H3O+ is going to do is it's going to protonate those O- that we just formed, all right, to give us the neutral product. So after your number 4 arrow, you're just going to put this so far. And I forgot to show the carbon-carbon bonds that were formed, right? So we took this acetylide with these electrons. They went and attacked. So I should have shown that before, right? That it went and those electrons in the bond formed the bond right there. And you draw everything else that is connected. So the carbon, and then that carbon is attached to CH3. And then you do the same thing. These electrons formed a bond. It's attached to a carbon, triple bonded to a carbon. And then that is attached to a CH3. Okay? So you formed carbon-carbon bonds, and the bond that got formed is these right here. Okay? So this is what would go in our box, actually. Okay? Any questions? No? Okay. If you have questions, just ask one of the tutors. Okay, so we'll move forward to the next one. Number 2, so we have a geminal dihalide, right? So we have these halogens coming off from the same carbon, okay? And so whenever we have that, you can create an alkyne with that, right? So on our arrow, do we have acid or base? KOH, OH minus, right? Don't let the potassium fool you. So it's OH minus, and that's a good base. It's a strong base. So what you're going to get, just like we described the sodium amide, right? In ANH2, you do 2 elimination reactions with the neighboring hydrogens, right? So you're going to abstract 1 hydrogen. Let me put these. Electrons go down, bromine leaves, do the same thing. Okay? And that's how you form those 2 pi bonds, right? You form the alkyne like that. But is KOH going to give us a terminal alkyne or an internal? Internal. Very good. So on our number 1, we're basically going to just take it like this. Boom, boom, right? So, 1, 2. Right, like that. So let's double check our number of carbons. So we have 1, 2, 3, 4, 5. So yeah. So we made sure that the number of carbons is still 5, and it's going to go in the internal position, not on the terminal position, okay? And it doesn't matter if you put it between 2 and 3 or 3 and 4, okay? It's still the same thing. It's still symmetrical, okay? So we created that internal triple bond. Okay, so let's look at our number 2. We have a lithium, elemental lithium, and we have ammonia. And ammonia would be in liquid, okay? So for this one, I don't really have too much of a trick for it, but you just have to know that what's going to happen to the alkyne is you're going to reduce the alkyne. And you're going to reduce it to what functional group? You're going to reduce it to an alkene. Started alkyne, increase the number of bonds to hydrogen, it becomes an alkene. And what's important, how we do that, so I'm going to put reducing, okay? And what's important is the stereochemistry of how you add those hydrogens, okay? That's what matters here. And you're going to add them trans to one another. So they're going to be coming from opposite sides, right? The two hydrogens that we're adding. So this can be compared to Lindlar's catalyst, if you remember that. So that would be just like H2 hydrogen gas with Lindlar's catalyst, right? Where they both take an alkyne and they reduce them to add those two hydrogens. But what's different is the stereochemistry. So this one right here, the lithium with liquid ammonia is going to give it trans. And then whenever you see something that's hydrogen gas with a metal like that, it's going to be syn, same side, okay? Relate that to all the others that have the metal too, okay? Think of a solid surface like this. Solid surface, this is your metal catalyst. And then if you were to have a double bond or triple bond, come and approach this metal catalyst, right? It's going to attach itself like this, right? Grab a hydrogen, right? Go down, grab the other hydrogen, and leave and release. Is it going to go like this, whoop, attach itself, then go like this and flip all the way around like that, and then come back? No. Did I just dab? Oh my God, I hate myself. So it's not going to do that, right? It's not going to be able to unattach and go in different orientations. It's just not as likely to happen. So use that to remember that with the catalyst, right? Whenever you have a metal, like a solid surface, it's going to add it from the same side. It's going to add it syn, okay? But here we have lithium and ammonia, liquid. It's going to add them from opposite sides, okay? So you take your double bond like that, add the methyl group that's coming. This is your 3 and 4 carbon, right? Then you do this group like that. Hydrogens get added, one here and one trans, okay? So this is our trans product. Okay, now we have 3. What's on our 3? What does that do to a double bond? Creates an epoxide, okay? It should be MCPBA. That might just be a typo. So it should be MCPBA, not MCBPA. And what you guys said, it's just going to create an epoxide. So where our double bond is located, it's going to give us this, like that, right? So this is like 1, 2, 3, 4, 5, right? So this is going to be our 3 and our 4 carbons, okay? And everything that was attached to those carbons are still going to be there, but you have to pay close attention to the stereochemistry of them, okay? So if they're going off of the same side, right? That's just a methyl, okay? So if they're coming up from the same side, like in our double bond right here, like in the, let me cut it kind of like that. They're both coming down. That means in our product, we're going to have them approaching the same direction. So they're both going to be on wedge, or they could both be on dash, whichever one you prefer, but as long as their relationship to one another is the same, right? If you put one on wedge, the other should be on wedge. If you put one on dash, the other should be on dash, okay? Okay, and then the groups that are both going up is an H and the CH3. Okay, so that would be our final product for number 3. And I tell some students like how to remember this is I used to live at Cougar Place, right? This down the street. So that was my house, that was my home. So I think of my house like this. It's my home, and then the oxygen is the sun for me, okay? I'm really sad. But I used to live there, so it worked, and it works for some people. Now I upgraded to a new place. So you remember, MCPBA, CP forms a house, oxygen is the sun, okay? All right, do you guys have any questions about that? No? Other than like, why are you such a loser?
So the lithium, LiH3, those are 2 separate.
I don't deserve you guys.
LiH3 is separate.
What?
That is separate.
They're put in at the same time. Whenever you see slash, they're put in at the same time. Whenever you see a slash between 2 things, it means that you're adding those things at the same time. Okay, so like lithium and liquid ammonia are added at the same time, okay? All right, let's go. Okay. Please. Okay, so for number 3, right, we're gonna look at what we have on the arrow, look at our functional group. We have an alkene in our molecule, right? And then on our arrow, number 1, we have this BH3 and THF complex. Okay, so this is one of those, you're not responsible really for the mechanism for this, but I want you guys to pair number 1 with number 2. Okay, so just a common trend, whenever you see hydrogen peroxide, or any peroxide really, like it could be this. Okay, that's a peroxide. And whenever you see that, it's going to form free radicals on its own. So let's put the bond so we can show the free radicals that are forming. Right? And you're going to have homolytic cleavage right in the middle. And one electron goes to one oxygen, the other electron goes to the other, okay? So you're forming these free radicals. That's why it's not good. Free radicals, and those are highly reactive. They're not good for us. So that's what you would get whenever you have peroxide, okay? And you guys know that normally the reactions like to take Markovnikov, right? Typically Markovnikov, typically anti, right? And if you have any questions about that, like make sure you ask because this is important. Whenever you see one of these reagents having a hydrogen peroxide or any peroxide, it's typically going to go opposite of the norm. Okay, so if the norm is that you want it to be Markovnikov product, right? It's going to go opposite. So just relate every time you see a peroxide, let that remind you that it is opposite. So it's going to be non-Mark instead of Mark, or anti-Mark instead of Mark, right? Those are the same thing, okay? I know Bean likes to use non-Mark, Meldonic likes to use anti-Mark. So if I say non-Mark, it means anti-Mark, okay? Same thing, okay? So you need to know that these two are going to be paired together always. So whenever you do your arrow, you want to put number 1 and number 2 as a pair, okay? And then what you need to know, this is hydroboration. And what that means, you're hydrating this alkene. And when I say hydrating, you're adding water across the double bond, right? So 1 carbon adds OH, 1 adds H, okay? And you just need to know that the OH, this is your source of OH, to remind you what's getting added. You need to know because peroxide in here, it will help to remind you that this is going to go non-Mark, okay? So that means the OH, when I say non-Mark, it means that that group, that nucleophile, whatever is coming and attacking, that's going to go to the lesser substituted carbon, all right? So we have this carbon and we have this carbon, right? So which one's lesser substituted, A or B? Or it's B. So that's what we're going to do. We're going to add that OH to that carbon. All right? And like, let's put it, yes. So it doesn't matter if you put it on a dash or on a wedge, but what matters is the relationship to the two, okay? On the key, she puts it on a dash, so I'll just put it on a dash so that when you come back and you look, you don't get confused or something, okay? So that OH is going to go to the lesser substituted one. And then on the same side, so syn, you're gonna get the hydrogen, okay? And they're both on the dash, right? Okay. So syn and non-marked. So I'll put syn as well. So we added that, and of course, like if the hydrogen is on a dash, then this group coming off is on a wedge. Sounds good? So now we'll move forward to our number 3 and see what we have. So we have PBr3, right? And over here, all we have is an alcohol, right? So PBr3 is a source of bromine, okay? So if you were to draw it out, for mechanism section, this is not important, but I think it helps to remember certain things if you can visualize it, right? So this phosphorus is a very strong electrophile due to all these dipole moments. It's very partially positive. And so there's going to be a reaction between this OH, so the oxygen, and that phosphorus, right? And we're not going to the mechanism, but what you do have to know is that this is an SN2 process, okay? And all that you're doing is, remember hydroxide, the OH, is that a good leaving group? OH minus, like if this were to leave, you would get OH minus. And is that stable? No, it's not stable, right? So the whole point of doing PBr3, and another reaction that we'll probably do later, is that you're trying to create a good leaving group out of OH, right? And that's the whole point. So you're basically that's supplying your bromine, and you're going to replace that hydroxy group with the bromine, okay? And if this is SN2, what's going to happen to our stereochemistry? Yes, so it's going to invert. So we'll leave everything on the molecule the same, like that, right? The upper carbon, nothing got touched there. It's just the hydroxy group where you have this SN2 reaction. So if you have the OH on a dash, right? So in our next product, the bromine, will it be on a dash or a wedge? Which one is it? Wedge. It'll be on a wedge, exactly. Because in our previous, in our reactant, we had on a dash, we're doing SN2, 100% inversion, like the umbrella. It inverts, you change the stereochemistry about that carbon, and then the bromine that now gets added, right, that's going to be on a wedge. Okay. So for number 4, we have NaCN, right, and CH3CN. So this is a spectator ion, remember that. So drawing this may help to remind yourself of what's going on here. So identify if the CN minus, is that a strong electrophile or strong nucleophile? It's a nucleophile because it has a minus charge on there, right? So strong nucleophiles like to undergo what type of reaction? And I'll give you some options. E1, E2, these guys are so important. Right? So SN1, SN2, E1, E2. Which ones like nucleophiles? SN1 and SN2. Which one likes a strong nucleophile? SN2. Make sure that whatever you have in your reactant, make sure that it's methyl, primary or secondary, and if it is, which it is here, then SN2 is going to happen. So you're going to have this cyanide, right? Remember when we did the mnemonic, like the bro, I really suck corn nuts thing? Remember that? This is the corn nuts. The corn nuts is coming back. So CN happens in one step and leaves. The bromine is going to leave. And you get inversion of the stereochemistry again. So again, this number, this carbon at the top, nothing changes. Hydrogen is still on dash, right? And then this carbon here, whatever comes and attacks is now going to be on a dash, where previously the leaving group was on a wedge. So it's going to be on a dash. It's the corn nuts. And then after that, we have on a wedge the hydrogen that's there. Right? You don't have to show that if you don't want to, but you can. Okay, so that's just SN2, right? Relate all the ones in, just in this problem, we did 2 that were SN2, right? So they're really important. I know we hate them, but they're really important. Okay, so let's move forward. Of course, anything for my girl Saida. She comes to every recitation. Here you go, is that good? All right, so let's do number 4. Sia. What the heck? Okay. We have an alkyne, right? Triple bond. And we have to figure out what the Cia2BH does to an alkyne. Okay? And this is another one of those. So remember when we had the BH3 in the previous question, we had the BH3 THF. I'll write it for you. BH3 THF tetrahydrofuran. And then in our number 2 step, we had H2, O2, OH minus. Doesn't that look a little bit similar to what we have here? Right? We have the BH, so there's some borane. And then there's also the hydrogen peroxide and OH minus. All right? So group these 2 together, right? Relate them to one another. So when we had this in the previous question, remember we said there's hydrogen peroxide. That's going to give us something that's non-marked. Right? And it's also going to be syn. We added OH. Right? This is very, very similar what's happening here. You're taking the alkyne, and don't worry about the mechanism. Just know what happens. And we're grouping these 2 together, Cia2BH and hydrogen peroxide. Okay? And you're adding water across this triple bond. What that means is one carbon is going to gain the carbonyl carbon, so this oxygen, right, and water. And then the other carbon will gain 2 hydrogens. Okay, the 2 carbons that are involved in the triple bond. So you're just adding water, H2O. If you remember water, hopefully that can help you to remember this reaction. Okay, and now you have to ask yourself, where is it getting added? So, like, which one's gaining our functional group, right? The carbonyls are functional group. So remember when we talked over here, we said it's going to give us non-marked. Same thing here. The functional group is going to go to the non-marked position. It's going to go to the lesser substituted carbon that is a part of the triple bond. So we'll put 1 and 2. We group these together. I put the 2 carbons involved in the triple bond, and then the lesser substituted one, the one on the right, is going to gain our functional group, which is the carbonyl. Okay? The other one, the one on the left, is going to gain the 2 hydrogens that are left in our water. So we're going to get an aldehyde, okay? Sounds good? And then that's for step number 1 and 2, and you want to show those together, okay? Let's move forward to number 3. So we have this organometallic where it has the alkyl chain attached to a metal, lithium, right? So is this going to be, this should remind you guys of the Grignard, okay? So is this going to be a strong nucleophile or electrophile? So it's attached to a lithium, right? And there's a huge difference in these electronegativities. So the electrons are going to lie more towards the carbon, right, than towards the metal, and that's going to give excess electron density on that carbon. So due to that, it's going to be a very strong nucleophile. It's even stronger than the Grignard, actually. So a nucleophile is going to come and react with something that's electrophilic. And what's electrophilic in our molecule? It's the carbonyl carbon, right? That's partially positive. So what's going to happen, I'll put the arrow right here. This, just like a Grignard, relate this to the Grignard, goes, attacks that carbonyl carbon, pi bond will come and become a lone pair. Okay. Oh, I've already put an arrow. So I'll put this carbon, became O minus, right? We attached, formed carbon-carbon bonds. So this is a CH2, CH3, right? And we had a hydrogen there previously, this one right here. So of course it's still gonna be there, didn't go. Okay, so this is another way to form carbon-carbon bonds. And then don't forget, in the arrow it shows us then H3O plus. H3O plus is it's an acid, so it's gonna come protonate or minus, give us hydroxyl, give us alcohol, okay? So that's what we're gonna get from that step, okay? And then number 4, we see a lot of oxygens, right? Right, there's a lot of oxygens. So let that remind you that this is gonna be an oxidizing agent, okay? So this is sodium dichromate. Okay. So sodium dichromate and H2SO4 says strong acid and H2O. That is an oxidizing agent that is very strong. Okay. And remember we said for our definition of oxidizing agent, it means you're increasing the number of bonds to oxygen, right, in some molecule. So that's exactly what we're gonna do over here, right? So right here we have an oxygen. So what's gonna happen between that carbon and that oxygen, you're going to increase the number of bonds to that oxygen. So we'll take everything else the same. This is the carbon with the OH. That's going to become carbonyl. And now we have a ketone. So we have the CH2 and CH3 from the other side. Okay, do you guys have any questions about that? Remember, this is an oxidizing agent, okay? Not at all, not at all. Yeah, for all those oxidizing agents, in fact, none of the mechanisms are really that important. Yeah, at all, yeah. You just need to know. Somehow. Yeah, exactly. Exactly. Sodium dichromate, strong. That's similar to Jones, right? They're both strong oxidizing reagents. And hopefully we'll use that later so we can explain it. So number 5, we have what is called an ester, okay? Remember we talked about the ether. And now we have an ester. So the difference between the two, ester looks like this. This is an ester functional group, okay? And then on our number 1, we have this lithium aluminium hydride. So lithium aluminium hydride, okay? And there's a lot of hydrogens, right? There's 4. So this is providing a source of 4 hydrides, right? Hydride is just a hydrogen with a lone pair minus charge, right? So it's a very, very strong nucleophile. That's very unstable. So that means that it's going to go and attack something that's electrophilic, right? Just like we saw in the Grignard, the organolithium. So you have this partially positive carbonyl carbon, right? So I'm going to draw the lithium aluminium hydride like that, right? And then this is the bond. I think it helps to know the mechanism for this one. You won't be asked in the mechanism section, but it's just the hydride, just like a Grignard. Boom, it goes and attacks that carbonyl carbon. Pi bond becomes lone pair, okay? And then this group, the ester that you have coming off, that is a good enough leaving group for the O minus that you would have formed there. Those electrons can come back down, push off the leaving group. So all at one time, I'll just draw it for explanation purpose. So that would have gone and left, okay? So nothing happened to our benzene. That's a benzene with a circle in it. Oops. So we said that this had come back down, so I'll put the carbonyl like it came back down. After the hydride came and attached itself, so this hydrogen that I'm showing, that aldehyde one, that's the hydride that came from the lithium aluminium hydride. When it attacked, pi bond becomes lone pair, comes back down, reforms this guy right here, okay? And then you got the O minus that got cleaved off, okay? And then after that, we do this again. So you'll have another source of hydride come attack right here. Pi bond becomes lone pair. You get another O minus, right? And another attachment of that hydrogen right here, okay? Another O minus, just like that. Okay, so we form two O minuses. So this lithium aluminium hydride is strong enough in order to go and attack an ester. If I use the reagent NaBH4, okay, with ethanol, like this, is that strong enough to go and react with the ester? So the answer is no. This is not strong enough to go and react with an ester. This is going to react with ketones and with aldehydes. It's going to react with those two guys, right? But if you have an ester like that, or you have an acid chloride, what's going to react, lithium aluminium hydride is strong enough of a reducing agent to go and attack that, okay? So think of like someone you know, like there's this girl named Layla, or Layla, right? And she's crazy, right? She's psycho, and she's strong enough to go and like rip everyone apart.
Product of step 1 is missing a carbon.
Oh, okay. Thanks. Thank you. Yeah, so Layla's psycho. You guys know someone named Layla? Is there someone named Layla here? No? Okay, so we're good. We're clear. I didn't offend anyone. So Layla or Layal, right? If you're Arab, you probably go to that restaurant Layal. Their toom is like really strong, right? Their garlic is really strong. Remember it, okay? It reacts with esters, right? And it's going to react with acid chlorides. But NaBH4, not as crazy as Layla, so it's going to react with just aldehydes and ketones, okay? So that's what we got over here, but don't forget, we have the H3O+, so that's going to come protonate. Protonate this guy, boom, boom. Protonate this one. And we got the right number of carbons now, that's 2. Okay, so we formed the primary alcohols, right? So now let's look at our number 2. And what we have, okay? So remember, spectator ion, so this is like that, right? And all you gotta know for this is like household bleach, right? So sodium hypochlorite, and that's household bleach that you use, I don't know, in your clothes or cleaning. And all that's gonna do is that's a strong oxidizing agent, or not super strong, but it's an oxidizing agent, right? Just let the oxygen remind you. And it's going to react particularly, right? You have to be very careful. A lot of students miss this. This NaOCl is going to react and oxidize secondary alcohols. Okay. Right here, is this a secondary alcohol? So it's not going to oxidize it, okay? It's very selective. It's going to oxidize secondary alcohols, right, to the ketone. And there's one extra exception, right? And this got a lot of students because, like, we don't go to class. So it's going to oxidize this carbon. So whenever you have the benzene, right, this benzylic position, okay? So if you have the OH right there, right, it's going to oxidize that, Okay, and this is what got a lot of students on this exam, because she mentioned it like right before the test and like no one was there. So it's going to oxidize that. So I'll put this arrow over here to show, and it's just different sources say different things, but for this, Queen Bean says it's going to go to an aldehyde, okay? So whatever Dr. Bean says, we follow it. Not blindly, but like. Okay. Right there. So that means that in this right over here, this was our step number 2. So in our box, put the aromatic ring. Right? And then this is the one that gets oxidized when it's at that position, okay? It gets oxidized. And then the other one, the primary alcohol, leave it as it is, and nothing's going to happen there. So you have the OH, okay? So that is the product. I don't know if this reaction is in the reaction sheet. So if it's not, just make note of it, okay? This one, the NaOCl. If it's not there, make note of it. Okay. Now let's look at number 6. And you have this benzene ring, and you have an alkene, and you're hitting it with HBr, okay? So this is a strong acid. So you're going to have a reaction between the strong acid and the alkene, okay? Attack right there, form bromide. And then you form a carbocation intermediate, right? So what's important for our reaction section is you need to ask yourself, where's the bromine going to go? Is it going to go to A, or is it going to go to B? It's going to go to the bromine, so you form bromide over here, right? So if you look at the mechanism for this, you would have formed some carbocation, so carbocation, right? Double bond opens, you know, it's going to go and attack that hydrogen. You form a positive charge on the A carbon, and then your bromine, your B carbon is the one that gains the hydrogen, right? And so that's because the secondary positive charge is more stable. Well, both of these are secondary, but it's more stabilized by this entire benzene ring, okay? So your positive charge, it's gonna go there, and then after that you have this bromide gonna come, boop, it's gonna attack. You attach the bromine. So this is the mark position. Mark just means the more substituted. Well, in this one we're comparing two secondaries. So let's see. In the key they will take off points if you put the bromine at the other one, okay? Because of the stabilization of the benzene ring onto that carbocation intermediate, okay? So that's what we're gonna get from our number 1. Right, bromine, this is addition of HX. 2 parking spots in the double bond, one gets the H, one gets the bromine. Okay, then we have Mg, and this is an example of an ether, right? Diethyl ether. And we went over that just creates our Grignard reagent, right? So the magnesium, it starts with M, so that's like your middleman, right? He goes right in between your alkyl halide and your halogen, your bromine. So you're gonna put that like that, draw everything else the same, and then wherever your bromine is coming off, put your middleman, the Mg right there, and Br. Okay, so we just created the Grignard, right? And that's our strong nucleophile Grignard. And that's number 2. Okay. And then step number 3. So remember earlier I was talking about like esters and acid chlorides and all that stuff. So right here, this is an example of an acid chloride. I probably should have drawn it out for you guys, but I'll do it now. So acid chloride, this is an example. So they call it that because this is a carboxylic acid, right? And if you were to replace the hydroxy group with a chlorine, acid chloride instead of carboxylic acid, okay? It's a derivative of those. Okay, so you just need to recognize that this carbonyl carbon is partially positive, right? And this is a strong nucleophile, very strong. So it's going to come attack, pi bond becomes lone pair, okay? Then this is gonna come back down. Push off. Chlorine is a good leaving group. So that's what's different between these acid chlorides. They have the chlorine on there, and that's a good leaving group. It's stable enough as Cl minus on its own. So that would have gotten pushed off. So you're basically forming a carbon-carbon bond. So I'll draw the Grignard piece right here. Okay, and that's the bond that, this bond right here. That's the one that we're gonna form. Okay, you hide your Mg and Br, and that pink highlighted bond is the one that we're forming to the carbonyl carbon. That right there. And that carbonyl carbon, right, it still has the CH2CH3 like it did before. And it lost the chlorine. So now you have a carbonyl carbon, right? Because that those lone pairs, it came back down to reform that carbonyl, right? And then after that, we still have electrophilic site present, right? So our Grignard will come and attack again. So whenever you have a good enough leaving group, and that's going to be like Cl minus, or that's going to be OR minus, they're stable enough in order for you to let them leave as a leaving group and reform that carbonyl. So you'll have your Grignard, right? Just like we did before, boom, comes and attacks. Pi bond becomes lone pair. You get a minus charge on that oxygen. So I'm showing this kind of in just to show the mechanism, but for this section you wouldn't have to do this. But I think if you draw the mechanism for this Grignard every single time, you make sure that you'll get it right. Okay, so that was the group that we're attaching the same group twice. So that's like, have this bond that has 1, 2, and you have this, and you have the benzene, like that. Okay, so you attach the same group, you attach it twice. So like when you're doing this on the exam, you don't have to like write all of this. What you do have to write is basically you have to have this arrow right here. Okay, and you need to put a 3 on this arrow, attach that group twice, right? So I can erase that for you guys. No, I'll just keep it just in case. But on your exam, you would be responsible for the 3 on this arrow. It's a full arrow that goes to what I put over here. And then don't forget, you have this acid workup step, and you're going to protonate that O minus. Okay? So you're going to get this, add the hydrogen, and you get that. Okay? And then basically this is what you're going to put in your box. Okay? Good leaving group. You're going to attach whatever that R group is. You're going to attach it twice. Okay? Any questions? Yes, ma'am. On the bottom or in the box? Whichever one looks more clear? Yeah, of course. I'll put it a little more pretty. And then I'll erase that trash that I just drew. Of course. Oops. I think every time I double tap, it changes to an eraser or something. I'm like, what's happening? Why is it not erasing? I'm just gonna wait. I'm gonna wait because I don't want to lose this. Like, that would be it. No, it didn't. I'm still trying to draw it, but I'm still trying to draw it, but I'm trying to click the eraser and it's not doing anything. So we're gonna stay chill. I broke your iPad, Chance. Where are you, Chance? I broke your iPad. No, I'm kidding. Come here. I just need your help because I'm clicking the eraser, but it's not doing anything. Maybe it does that sometimes.
So are you just? Is it
I'm
just
trying
stuck?
to click
What
the
is-
eraser. Try to erase right there. Yeah. What the hell?
erased.
It wasn't working for me. It wasn't
Weird.
working. I
Some-
swear
yeah,
to
I don't know.
God.
Sometimes it just doesn't.
You gotta
It
change
might-
it. It knows its owner.
True. Yeah.
It knows. That's so
The Apple
weird.
Pencil chooses the wizard.
That's so weird. He has the magic touch, I swear. Yeah, it's working now. I needed you. What a guy. Okay, so, sorry, what was your question? I don't know your name. What was your question? That's your product. Didn't you have a question? Well, you all have glasses. All four of you guys have glasses.
I was just asking him those because I saw the but then I don't think
No, they're not connected. There's a space, like right here, you mean?
Yeah,
Yeah, there's a space. I was glitching with the eraser.
that's what I was asking them.
For sure. And I'm going to erase this, what I put over here. Erase this. All right. So really, what you got to put on your exam is just like that, okay? 2 of those attached, yeah.
So 3 are like the product that 3
Exactly. It includes the protonation step as well, and it includes both of them being attacked. My girl Saida wants me to zoom out. The whole thing? And we're gonna post this. We're gonna post this like on the ACS website afterwards. So like, don't worry too much about pictures if you didn't get one. What? Okay, we did reactions. Yeah. All right, almost 9. We're okay. And if you guys have to go, go do whatever you have to do. It looks like the video is still working, and hopefully that one is too. So we're gonna do mechanism. Let's do mechanism. All right, guys, we're gonna do mechanism. Okay, so because I can't even hear myself. Okay, please, if you love me. Okay, so right here for mechanism, this is what gets a lot of students. Okay, so you want to look at your reactants and you want to compare it to your products. Right? We have product A and we have product B. Okay, I'm not gonna touch it, and then I'm gonna try it again. There we go. A and B. Yes. Okay, so we want to form both of these, and you gotta identify what is different. Yes, sir. Of course. So you gotta identify what's different between your reactants and your products, right? So it really looks like this ring over here. I think it's because I'm double tapping, it's stopping like that. I'm just not gonna touch it. Chance, touch it.
If you tap the pencil itself twice, it'll switch between the eraser and
Type tap. Tap tap. Ooh.
Yeah. So you can change it from there.
Tap tap. Ooh.
that might
So
be
much
what's
power. I think so. Okay, thank you. So we have, I was trying to go to a highlighter, but it's okay. Is there a tap tap for that? I guess not. Okay. And I'm drawing. Chance. I'm drawing. And nothing's happening. Well, I swear to God, he's gonna touch it and it's gonna work.
Yeah, sorry for being such a pain.
No, are you kidding me? If it weren't for you, I wouldn't even have an iPad. I have nothing.
Oh, this got unscrewed. That's why the pencil is unscrewed.
Oh, that's
Cheers,
my
Seth.
bad.
No, no, you're good.
That is my bad. Thank you so much. That's my bad. Okay, so we were trying to identify this right here, this ring. Doesn't it look the exact same as this? Right? Yeah, so that's going to be when we're going to our first product that looks the exact same. And it shows that this OH over here, that as well is somehow going to leave, right? So it goes away somehow, and that should be a clue to you guys. If you see the OH is leaving, most likely the first thing that happens is that oxygen with its lone pairs goes and attacks something, okay, to form water as a good leaving group. Now, let's look at what's on our arrow. And on our arrow, we need to identify what are our good nucleophiles, what are our good electrophiles. So we have H2SO4, and this H is partially positive, right? And then on our reactant, what are our nucleophiles? We have a double bond, that's a nucleophile, right? Those pi electrons are nucleophilic. And then you also have the lone pair on the oxygen. So that's what you have to identify. Whatever is nucleophilic and whatever is electrophilic right away. Because those are the things that are going to react with one another, right? Negative likes positive. So let's say if you're unsure of where to start and whatever it is. I mean, first of all, we don't see anything even happening right here with this double bond. So for now, I'm not going to use it, but let's do a guess and check, right? So if this were to come and abstract the hydrogen, push electrons onto the oxygen, right? Then one of those carbons would gain the hydrogen, and the other one would lose that electron, so it would gain a positive charge, right? And then all that's really left to do is reform the double bond, which obviously we're not going to do that, and then, or this nucleophile would come and attack that. Okay, I'll draw that out because I feel like me just talking is not going to help you guys. So let's say we used our double bond to go and attack. So a lot of students have problems with the first step. What do I do in the first step? And once they get that first step, they know the rest of it, right? So that if that goes and attacks there, right, you would put the hydrogen on the lesser substituted carbon, right? And then the one that lost that pi electron, it would gain the positive charge, right? So once we get that, we already said we're not going to reform the double bond, right? And the only thing that's left that's nucleophilic would be that oxygen on the hydroxy, right? So if that were to come and attack, it would form this long ring, and then we would form an ether, right? And that's not what we have in our products. We're trying to get to these guys, and we don't have that in our products. So that's the reason why I'm not picking the double bond to go and attack first. That's the reason why I picked my other nucleophile, which is the oxygen with the lone pairs. That's going to go get the hydrogen, and then the electrons in that bond go onto the oxygen, okay? So what do we get after we do that? We're going to get nothing happened to double bond. Draw everything else the same. What just happened? Okay. So that looks the same. This oxygen, it grabbed the proton, so we're going to put that. And then it still has that other lone pair that's present. So now it's going to have a positive charge, right? So now we have formed water as a good leaving group, right? So this reaction, you can probably see where it's going. It's going this E1 route. So this is you had an alcohol before, you don't have it anymore, and you have an acid. So you have acid, that's the acid, catalyzed, dehydration, removal of water, and then you'll say of alcohol, right? So the name is telling you all the steps that we're going to have to do here, right? And so once we form that water as a good leaving group, so if it were to leave, a good leaving group leaves, right? So if this were to leave and go on to the oxygen, what degree carbocation would we be forming? When I say what degree, I mean like tertiary, secondary, primary. So it's like this carbon right there. You probably can't even see me highlighting it, that one. So if that water were to leave, okay, that water were to leave, takes these electrons with it in the bond. I need to highlight it because I feel like you guys can't see what I'm pointing to. That one, okay? Then that remaining carbon that's left there would get a positive charge, right? And so that positive charge is on a carbon that is attached to only one carbon. So it'd be primary, right? So that's a primary carbocation. And our primary carbocations, are they stable? Mm-mm. So if they're not stable, then we got to do something that will promote this reaction to form a primary carbocation. And this is very important because this right here is 4 points, all right? So don't form, if it's primary, you have to do a hydride shift in the same step. Like same time, right? So if you just formed the primary carbocation and you didn't use the hydride shift to boom, push off that water, then you get -4 for that. And a lot of students made that mistake. I made that mistake. So don't make that mistake, you know? I mean, now I don't really care. But at the time, I was upset. So don't make that mistake. Same time, okay? You cannot form that primary carbocation on its own like that. So in the previous one, let's show that hydride shift. So this came, moved over there, pushed off the leaving group as water. So what that does is instead of giving you primary, right? Instead of giving the primary carbocation, instead puts it right there, right? And you guys agree like that's tertiary? Tertiary must stable. So, and the hydrogen that was moved is this one right here. You can put it, you don't have to put it. Okay? We formed the carbocation, and that's good. You always want to form carbocations in these because that's where you can have rearrangement, that's where you can have ring expansion or ring formation, right? So we have our carbocation, and let's look at what we have in our A product. Our A product has the formation of a ring. So what are we going to use to form the ring? You're going to have the nucleophile, which is the pi bond, go and attack that positive carbon. So this right here. Like that. So let's count this out. So if we were to take this to be the number 1 carbon, number 2, number 3, number 4, number 5, and number 6. Okay. Doesn't our product have a 6-membered ring? So that's exactly what we would get if we had our double bond like a door hinge, like this, and you went whoop, and it went and it attacked that number 6 carbon. So the door hinge basically is that number 1 carbon. That's the one that's keeping the bond, and the one that's losing the pi bond is going to be the number 2. Okay, so we're just going to redraw that, what we said. So redraw the ring, right, and it's 6-membered, and we're going to go through and number all the carbons, right, just to make sure that there were no mistakes made. So that one right there where they connect, that's our number 1. And that one kept this new bond that was formed. So we formed a bond between 1 and the one with the positive charge, that's the 6. So I put that as 6. Okay, we formed that bond right there. And then 6 is still connected to the methyl, and as well as this other methyl that has that hydrogen that I'm showing, it also has that one. And then 6 is still connected to 5. And what is 5 connected to? 4. Good. And then 4 is still connected to 3. And 3 is still connected to 2. So where the change here was the pi bond in between 2 and 1. Right? So 2 lost the electron in the pi bond. So if it lost electron, what charge should it get? Positive. Very good. So you have that tertiary. Now let us look at our product. So we have a double bond that is forming between, let's keep the numbering the same, we have a double bond that's forming between 1 and 2, right? So that means we need to do elimination, right? So this is E1, we formed the intermediate. You got to pick a hydrogen. Oop, it shouldn't be coming from that one. that's adjacent to the positive charge. This one right there. You're going to use some base that you have in here. Remember, we formed water as a good leaving group. So we can just use water. What else can you use? Exactly. You can use the conjugate base of the sulfuric acid. Right? This would be the conjugate base that you can use. Both of them are good. You just have to use some weak base. Right? So you can use that to come and do this abstraction of the proton, or you can do the H2O. Right? Use H2O, and then that would collapse the electrons onto where that positive charge is, get rid of the positive charge, becomes neutral, and then that's how we're going to form our number A, or letter A product, okay?
So when it combines into two rings, the double bond is lost.
Yeah, exactly. So it's like your pi bond. He said, is the double bond lost? Yeah, so it's like the pi bond. It goes like a door hinge and it attacks the positive charge. So that creates a sigma bond now instead of the pi bond that used to be there. Okay, good question. So now we still have to get B, right? So how can we do that? So it looks like, okay, our methyls are in the same place. Right? And all you got to do, you can use the same carbocation intermediate that you just created. Let's, we don't want to miss any points. So we'll just say like redraw, or we'll put the 3 lines to represent like the same thing. This is the same thing that I'm drawing. You got this. This goes like this. Draw everything the exact same. Positive charge here. And then you're trying to get the double bond to form in a different location. You're going to do the same idea. The only difference is you're going to abstract the hydrogen from the other carbon from the other side and collapse the electrons to form the double bond where it is in our product. Okay, and you can use also weak base. Let's do with water again. Abstract this hydrogen. Electrons collapse onto the positive and we form the double bonds right there for B. Okay? Do you guys have any questions about this? Not at all? Okay, if you have any questions, please feel free to ask, or ask Chance as well. That's the whole mechanism. Okay. So we're almost there, guys. We're almost there. Good job so far. So we're going to do the synthesis. And of course, with synthesis, there's several different, ways that you can create that product. So if you have a way that you propose and you want to show it to us so we can check in and see if that looks really good, feel free to, because there's different ways. I did a different way than what's presented on the key for Dr. Bean, okay? So do whichever way you remember and whatever floats your boat. So honestly, whatever you can remember, do that, okay? So we're going to read the instructions. So it says synthesize the molecule below from alcohols or alkenes of 3 carbons or less, right? So on the right, I like to just start off by writing my toolbox, of what I can get back to. So it says alcohols of 3 carbons or less. I'm going to put 1, 2, 3, right? So that's an alcohol. It's going to be equivalent to that or less. And then also you can have an alkene. So like this. 1, whoop. What was that? So we said 3 carbons or less. So I'm going to remove 1. That's 3 carbons. So less than that. 3 carbons. Okay. And then what we want to do, the hardest part is identifying that first step, right? The last thing that you formed, because we're going backwards. So you want to look at what you have on your molecule and identify the different functional groups that you have, right? So what functional group do we have on here? This. We have a carbonyl, right? And more specifically, it's an aldehyde carbonyl, right? So you need to think in your head, what could I have had before, and do something to that and make it into an aldehyde, right? Not a carboxylic acid, an aldehyde. So for those in Miljonic's class, or Dr. Meljonic's class, he did not discuss PCC. So if you have a different way to do it and you want to show it without using PCC, feel free. But doing PCC right now will allow us to do this in the least amount of steps, okay? So PCC, what is it? It's just an oxidizing agent, and it's a weak oxidizing agent. So I'll put it in the arrow, and then I'll explain a little bit. So I just saw that there's a carbonyl, right? So it's been oxidized by something. If it was an alcohol before, right? We increase the number of bonds to oxygen to make it a carbonyl. So I'll put PCC, draw everything that I have analogous, the same, and then have that as a primary alcohol, right? Instead of that aldehyde. So when you have this primary alcohol, you hit it with PCC, right? Not Jones, not sodium dichromate. Those are also oxidizing agents. PCC will make it stop at the aldehyde. So let me write on just a side note. You're going to see this a lot. Jones ox is going to be a strong ox reagent. Has ox in the name. But Jones reagent is going to be strong. So when I say strong, that means that if you start, for example, with this primary alcohol, right? That means it's going to oxidize all the way, that's a 3, all the way into the carboxylic acid. That's what that means, okay? You oxidize it to its maximum, right, without cleaving it. And then if you have PCC, so we said PCC is the weaker one, so it's weak. And what it's going to do is instead of taking it from the primary to a carboxylic acid, it stops right at the aldehyde and doesn't oxidize it any further. So you write the same idea, except you stop it at the hydrogen, okay? So I used to remember this just because, like, I'm a Mac user, so I think Macs are, like, dominant to PCs, so I'm like, PCs are weaker, right? If that works for you, like, use it. PCC is the weaker one, so you can remember that. If that works. The things I come up with is crazy. But, I mean, it's so much stuff that you got to remember, so you got to figure out some way, Whatever works for you, use that. So, No, I don't want to upset anyone. I just want everyone to get, like, A+ on their test, so that's all I want. I would be very happy if everyone did well. So we used PCC, got it to the aldehyde. Now we have an alcohol. Whenever you see an alcohol, I want that to trigger a special word, and that word is Grignard. Okay? I want it to right away, instantaneously, whenever you see alcohol, before that, we want a Grignard. Because a Grignard reaction will result in an alcohol. Okay? So you can do this different ways. But let's say that this is the bond that's formed, right? And we'll make our Grignard piece. The Grignard, remember, it has magnesium and bromide, and that got attached. I'm saying that it got attached to this one. But wait, like if you have a carbonyl, doesn't that mean that the bond should form directly with that carbonyl? But you can save yourself some steps by using an epoxide instead, using an epoxide opening, because you can use 2 carbons. So I'll highlight the carbons. And these 2, instead of adding it, having to do an extra step of Grignard, let's just make an epoxide like this. Remember my house? It's CP. So we're going to use that, and we're going to use the Grignard to go and attack one of these. Oop. Push the electrons onto the oxygen, it opens like a spring, and then you get minus charge on that oxygen, right? So what do we have to include on our arrow? If we don't have a minus charge right here, right? We have it protonated. Then H plus, and you said the then. The then is so important. That's points right there. You have to add these at separate times, right? Separate times, then. Yes, sir.
The Grignard reagent and an epoxy.
Exactly. So have you wanted to not use, let's say you forgot about epoxide and you wanted to have it attack a carbonyl, you can just use formaldehyde like that, right? And have the Grignard go and attack directly. And you'd use a different Grignard, but the epoxide gets it to what you want in less steps. Okay, so it's going to attack the carbon that's 1 over from the alcohol, so the beta. Right? If this is your alpha, you're gonna attack that one, okay? So let's deal with the left side first. Let's deal with the epoxide because I think it's easier. So what reagent do we use to form an epoxide? Exactly. So he said MCPBA, and what our functional group has to be before that is we want it to be an alkene. And are we allowed to start with alkenes? Yes, it says that 3 carbons or less of alkenes, so that looks good. Right, we finished that piece. Yeah, or you can draw it out if you want. Okay, so on the other side, what do we have? We form the Grignard. So you need to ask yourself, how can I form a Grignard? And what you want to use is magnesium in ether. Exactly. So you're gonna go 1, 2, boom, that piece, and then you added that magnesium middleman right in the middle. So you're just gonna have the bromine coming out. Right? That's how you do that. Okay, so now we have a bromine, but we're trying to get this down to 3 carbons or less. And do we have 3 carbons or less? No, we still have 5. So that means when you see that, it should give you a clue that you still have to form more carbon-to-carbon bonds. You still have to do that. So that means we have to go back to a Grignard, right? So it will hopefully when you do more and more, it'll be repetitive in terms of the Grignard. You're always going to go back to a Grignard. So that means a Grignard would result in an alcohol, right? So we want to, before the bromine, we want to have an alcohol on that carbon, a hydroxy group, right? So we need to have this. We need to have this. And we want to replace that hydroxy group, right, with the bromine. So there's 2 different ways which you can do that substitution. And we want to pay attention to the degree of our alcohol. So if our alcohol right here, right, this is the carbon that I'm talking about, that one right there, it's connected to 2 carbons. So that means it is A-okay if you want to use PBr3, that is okay, right? If you wanted to use the HBr with 0 degrees in ether, that is okay as well. So let's just go with PBr3. PBr3, right? So this is an SN2 reaction where you're replacing that hydroxy group. Remember, like we said, hydroxy is not a good leaving group. You're replacing it with a bromine. And that's what PBr3 does, okay? It's going to be your best friend because it gives us an alcohol before. And then, so we form this alcohol so that we can do a Grignard, right? So now we want to come up with our 2 pieces. So we will pick which. It makes sense to form this bond because we want our Grignard to be the longer carbon chain. Doesn't matter, right? But it would just require less steps to do that if you were to try it out the other way. So let's make the right piece. Let's make that our Grignard reagent, okay? So 1, 2, and it's directly attached to the magnesium with a bromine. Does anyone have any questions so far? Or we're good? We're okay? And at the end, like, ask whatever you want. So that's the Grignard reagent. Put a plus, and we have this, right? That's supposed to be a carbonyl before, with a hydrogen like that, okay? And I can even try to draw it sideways, maybe, if that helps. I mean, I probably shouldn't do that, but whatever. We'll do it anyway. Just so you guys can see, like, how it's coming and attacking, I guess. So this is like the CH3, right? And this right here, there was a hydrogen. So this Grignard reagent came like this. It went like that. And then what do we have to include on our arrow? Protonation. We have to protonate that minus charge on the oxygen, right? And then that would have formed a bond between that carbonyl carbon and the Grignard there. And it still has the CH3. So like this is like the remainder, and this is right there, okay? And then the one that's crossed is the one that we formed. So I'm gonna draw it, normal. So we'll put CH3. We said it was touch of carbonyl. We had it as an aldehyde. Okay, so now let's do this. Let's do the left side. So remember, we stopped at an aldehyde, and it says that we can have alcohols before. So which oxidizing agent do we want to use? Which one's weaker?
PCC.
PCC. PCC is the weaker one. So we draw the 2 carbons that were there, 2 carbons here. We hit it with a weak oxidizing agent, PCC, and that's going to oxidize it to the aldehyde, and it stops at the aldehyde. And then we can have the ethanol. That's okay for our starting. So we're good to continue to the other piece. Now we have to create the Grignard, right? So how do we create a Grignard?
Magnesium.
I love this guy. I appreciate you. So,
I appreciate you.
okay, so we have this bromine here, and basically we added that magnesium right in the middle, all right? So then what we want to do is, how can we add that bromine there, right? So we're not going to do Br2 and light, right? Because that wouldn't give us the bromine in the more substituted position, right? So remember I said that PBr3 is really helpful to use because you can get it down to the alcohol and make the alcohol the hydroxy. You can make it a better leaving group by doing PBr3. And all we want to confirm is if right there, this carbon right there, make sure that it's primary. And if it's primary, then it's going to go SN2 with no problems. And you can use PBr3 because this is SN2, right? And we wanted to get it down to an alcohol of 3 carbons, right? And that's what we got. So, all right, I'll zoom out. That's what we got. Feel free to leave or whatever. If you have any questions, stay. All right? Here, let me cancel this. 1 second. And I don't want to make it seem like I don't.